If you take a modified dart and place it in the barrel of a pressurized air cannon, when the valve is open, the dart should be propelled across the room and get a bullseye on this dartboard. But the question is, what score will it actually get? Welcome back to Engineered Bets. Today's line is over under 3.1 points, which is slightly more than Bronny's career high in the NBA. As a reminder, these intersections count as triple and these outer ones are double, so keep that in mind when making your prediction. A regular dart can stay straight because its weight is more concentrated to the front, and this lighter four-pronged wing called a flight helps keep it straight. Without it, the dart doesn't work nearly as well, if at all. So when making the dart, I added a small fishing weight towards the front and glued the tip of attack. Then to help it fly straight, I taped an additional body to make it longer. To make a better seal with the barrel, I added some tape to the front, and lastly I glued the back hole. With these modifications, I had some confidence that the dart should fly straight enough to stick to the board. Next, I had to decide what height I should put the dartboard if I want the dart to get a bullseye when launched from about 2.7 meters away from the tip of the dart as it exits and at an angle of roughly 17 degrees. To solve for this height, I first estimated the work done on the dart during the expansion, which I then used to determine the dart's exit velocity. Lastly, I solved for the trajectory using Newton's second law to factor in gravity and drag. I've already done similar calculations for these last two parts in previous videos, so I'm going to mostly focus on the work part. When the valve is open, the compressed air will rapidly expand, and as it does, the air pressure will act on the cross-sectional area of the dart, resulting in a force that will accelerate the dart until it exits the barrel. If this force was a constant, it would look like this graphically, and I could calculate the work done on the dart simply by multiplying that force times the change in distance, which is the area under this curve. Unfortunately, it's not so simple, since the pressure and therefore the force is highest at the start and then decreases as the air expands. So this simplified equation can't be used, but rather I need to integrate the force with respect to distance, which gets me the area under this curve no matter what the path looks like. It'll be easier to solve for this unknown path if I use pressure instead, and since the force is the pressure times the constant cross-sectional area, I'll plug that in and rearrange to get the other very common equation for calculating work, which is the integral of the pressure with respect to volume. I know the initial pressure is 60 psi because that's what I decided to pressurize it to, and I also know the initial and final volumes just from measuring. But I still don't know how that pressure changes as it expands to the final volume. Maybe it drops steeply and then levels out, or maybe it's nearly linear. To solve for this unknown path, I'll use a version of the polytropic equation for an ideal gas that adiabatically expands, meaning the expansion happens so rapidly that there isn't time for heat to transfer to the air. This equation says that at any single point during the expansion, its pressure times its volume raised to a constant gamma is equal to a constant value. This constant gamma just lets me use this equation for different gases, but I'm using air in this example, so it's just 1.4. Anyway, I'll solve for this unknown constant using the initial pressure and volume values, which as discussed earlier are known. Now that I do know what this constant value is at any time during the expansion, I can plug it back into the original equation. Now if I solve for this pressure as a function of volume, I do know how the pressure changes with volume, which was the path I was solving for. And when plotted on the graph, it looks like this for all volumes. So to calculate the work done on the dart as the air expands, which remember is the area under this curve, I simply integrate the pressure function from the initial volume to the final volume, which after using some calculus and lastly plugging in all these known values, got me about 13 joules. That's the energy that was added to the dart, and the next step was to determine the velocity of the dart at the exit. As mentioned, I've done similar calculations in previous videos, so I'll just summarize by saying I took the dart's initial energy and added the work done on the dart to get the dart's final energy. After solving for the exit velocity, I got that the dart should be traveling at about 63 meters per second when it exits the barrel. Finally, with this velocity, I can now use Newton's second law to solve for the trajectory of the dart. I'll be using the same steps as my last golf ball launching video, so this time I'll try to summarize it in a different way, which hopefully will make the steps clearer if you were a bit lost last time. Newton's second law lets me solve for the acceleration of the dart by summing the forces acting on the dart, which in this example I'll account for the constant force due to gravity pulling down on the dart and the force of drag opposing its movement. The drag force equation is a function of velocity, so as the dart slows down over time as it flies through the air, this drag force will also be decreasing. That means when calculating the acceleration, I can't just do it once, but rather I need to keep updating it throughout the flight as the acceleration changes. So, showing the actual flow through the iterations, I start with what I do know, the initial velocity from the last part, and I plug it into the drag equation where I chose to model the dart as a cylinder, so a drag coefficient of 0.85. This gets me the initial drag force on the dart. Then plugging that drag force into Newton's second law allows me to get the initial acceleration. Next, I want to do these steps all over again for the next velocity, but I actually don't know what that velocity is quite yet. If I assume the dart accelerates at the initial rate I just calculated for a super small time step delta t, then I can get the next velocity, because rearranging the definition of constant acceleration, I see that simply multiplying that acceleration times delta t gets me the change in velocity across this step. So I can just add that to the initial velocity to get the next velocity. Now with this next velocity, I can start the process all over again and continue indefinitely. Here's what the actual calculations look like, where instead of 2D vectors, I split it up into x and y components and plotted the values on graphs. At each step, I also updated the position graphs in a similar way using the initial position of the dart and the general definition of velocity, which lets me integrate the velocity curve to get the change in position. Showing this being solved, and we've got a good sense of the trajectory. But in case I chose too large of a time step, I did it again with a much smaller one to minimize numerical error. Anyway, I now see that the dart should reach the dartboard 0.045 seconds after launch, and after traveling in the air that long, it'll be at a height of 1.07 meters. So that's where the bullseye of the dartboard was placed. To hopefully avoid alignment issues, I attached a laser to the barrel, and these PVC valves can be tough to open, so I made this jig to hopefully open it as quickly as possible. Vegas was pretty skeptical of some of these assumptions, so they set the line at 3.1 points, factoring in the odds of the score being doubled, tripled, flying off course, and also the dart not sticking to the board, which would result in a score of 0. Last chance to lock in your guess in the comments, and I'd love to hear your thought process behind it. And now it's time to see what actually happened. After opening the valve, the dart shot out somewhat straight and did stick to the board, resulting in a score of 15 points. That means the over has hit. Congrats to those who got it right. Although it won't officially count, I was curious, so I decided to try it a couple more times to see if it was at all consistent. And it turns out the only consistency was the dart's hatred of under, scoring 19 points and 12 points in the following 2 attempts. Since it did get somewhat close, you might be thinking this was a pretty good estimate, but it really wasn't. From some post-attempt analysis, the average velocity of the dart was much slower, but it didn't matter that much as long as the dart traveled fast, because then there wouldn't be much of a drop. There's so many factors that led to the dart's deviation, so let me know in the comments which one you think played the biggest role. Thanks for watching to the end, and I'll see you next time.